The last few sessions we were talking about various proof types, methods, strategies of going about proving things. There are various ways to prove things, various techniques, if you like. And we did the first of three in the previous session. First one was proof by construction, meaning to prove that a certain kind of mathematical object, entity, exists with certain properties. Well, to prove that it exists, you actually build one, you construct it. So in a sense you're creating an existence proof, right? So we finished that one. Now this board, so the next four sessions, this one and the next three, on the second and third, proof types, proof methods. The second one is called proof by contradiction. You can probably guess what it's about. And the third one is on, let's see, so it'll be the next session, on proof by induction. It's a bit more complicated to explain. I can't give you that in one sentence, but we'll come on to it soon enough. Alright, so the second one is proof by contradiction, and it's used a lot. Proof by construction, sometimes. But probably of these three, just from my own experience, just because one of my interests, strong interest, is group theory of groups, finite groups, particularly finite simple groups, which are a certain specialized category of finite groups, with a finite number of elements in the group, in the set. I'd say that proof by contradiction, probably the most used. Induction, gets used, probably less frequently. Proof by construction, haven't used that much at all. So, anyway, okay. So the second one, proof by contradiction. How does that work? What's the basic idea, the basic strategy? What are you doing? Well, as its name suggests, say you're trying to prove some mathematical statement, P, whatever it is. So using this strategy, this kind of proof, you start with the opposite. You start with not P, right? And hence, that's why it's called contradiction. You have contradicted P by starting with not P, the opposite. And then from that, you conclude something, let's say, so if not P, then, arrow, then Q, so Q is some other statement. But in reality, not Q is true. In other words, you have deduced from not P, then Q, but Q's false. I mean, the reality is that it's not Q. Now, there's some logic. It's a piece of symbolic logic called modus tollens. Now I'll come on to it. I'm just sort of giving you an overview at the moment. Now modus tollens says if A then B, but not B, well then you can conclude that not A. For example, a concrete example. If you live in Xiamen, that's the city where I live, if you live in Xiamen, you live in China. But you don't live in China, therefore you don't live in Xiamen. It's sort of common sense. But that type of reasoning, that type of logic, gets a label. It's called, Latin label I guess, modus tollens. I'm not quite sure what that means in Latin. Probably some method of contradiction, or I don't know. Alright. So okay, so getting back to the proof by contradiction. You're trying to prove P. the method you use, when you use proof by contradiction, is to start with not P. The opposite, the contrary of the falsification of P. So you start with not P, and from that you derive Q. But Q's not the case. What's real is not Q, and therefore you're using modus tollens. You therefore negate what you started with. Now, what you started with was not Q. So in other words, you have not double not Q, and hence Q. Sorry. You have not P, and hence P, which is what you wanted to prove. Right? So that's how you prove it. So you prove, effectively you're proving P by getting a double not, by getting a NOT, a not P. You derive not P. So that's the idea in a sort of hand-wavy overview sort of style, and I'll repeat myself somewhat, but in giving the details. Now in the text, here's a fairly simple, almost verbal type reasoning in the textbook by what's his name? Sipser. Okay, so it's exercise chapter 0.23. Oh, by the way, when we finish this board, these next 4 sessions, that's the end of this preparatory chapter, the end of chapter 0. And so the next sessions will be problem solving. Now, I think problem's fairly easy. This book starts off fairly easy, like about junior level, I think. So I'll just solve these problems in real time, I think, on the board. Get through them fairly quickly. It's later in the text with the theorems get much heavier, well into M1 level, master's level. All right. So here's an example, 0.23, same numbering as in the text. Now, so you're talking about Jack and Jill. If you're not native English speakers, Jack and Jill are childhood characters in child readers, early booklets for teaching children how to read, like 6-year-olds or something. Jack and Jill went up the hill to fetch a pail, a bucket, a pail of water. Jack fell down and broke his crown, that means his forehead, his head, and Jill came tumbling after. Okay, so I can even remember it from, not even childhood days, but from kindergarten days. All right, it's so famous. Okay. All right, so Jack sees a dry Jill. Jill is not wet, right? She didn't get wet by the rain. Okay, so he concludes, Jack concludes that it's not raining. Meaning outside, assuming Jill has just come in from outside, okay, and she is not wet. She doesn't have a wet umbrella or clothes not wet. She's dry. Okay, so